Hello everyone, my name is Zora Doljanin and today I'm going to present you an article called Quantitative Measures for Classification of Human Upper Body Posture in Video Signal to Improve Online Learning. During the COVID-19 pandemic, online learning has emerged as the predominant education model, which resulted in the need to develop methods for efficient estimation and classification of students' attention and engagement based on readily available visual information. We envisioned a new system for automated assessment of students' attention in a form of an adaptive intelligent agent for e-learning. In our work, we want to detect students and monitor their body language and facial expressions using three technologies: human pose estimation, emotion recognition from facial expressions, and person detection in images. Our main objectives are, firstly, to collect data from students' web cameras during an online class. Secondly, to assess their learning performances based on behavioral patterns. And finally, to enable customization of individual learning curves. The most important topics covered in our work are creating student pose estimation dataset, proposing features for estimation of emotion and attention from human upper body posture detection, and conducting online learning pose estimation experiment. Body language and posture can provide great insight into students' levels of attention. For example, leaning forward and taking notes signal higher levels of attention, while leaning back, yawning, supporting head, or looking away signal lower levels of attention. We created a new dataset containing 16 pictures capturing a variety of human torso poses within a web camera field of view, with many realistic challenges, such as various degrees of head and body rotation, partly visible body parts, poor lighting, etc. Then we conducted an experiment in order to test the robustness of the pose estimation method in critical scenarios highly likely to occur in online education. Our method used the Open Pose 18 key point detection model. For each processed image, we analyzed the number of true positive, true negative, false positive, and false negative key points detected in an image in order to measure three metrics as indicators of pose estimation success rate. Those were accuracy, true positive rate, and F1 score. The dataset is segmented in two categories: attention-affiliated poses and attention-aversive poses. It is believed that the poses in the first category indicate higher levels of attention, whereas the second category points to the lack of interest. The most common attention-affiliated poses are those with IDs equal to 5 and 15, where the upper part of a person's body is clearly visible and orthogonal to the camera. These poses may be considered attention-positive, effective, neutral, and typical to video lectures. Also, additional 4 poses with IDs equal to 4, 7, 8, and 12 could also be classified as neutral poses, common in video lectures, although upper body key points are not clearly visible. In all of these 6 poses, a person participating in an online lecture is sitting down in front of the computer. It is expected that in these poses, the student is actively engaged in the class. All other poses are indicative of some activity that is not directed at the lecture, expressing the lack of interest for the online class. We proposed a set of 22 different features or measures for estimation of emotion and attention. All of the features are determined from the upper body key points. Features with IDs 1 through 5 are directly observable from the estimated key points, using the Open Pose system or a similar API, while features with IDs 6 through 22 must be derived from the poses classified from the observed key points, measuring the rate or frequency by which a student is assuming one of the poses. The proposed features can be divided into two groups: key points-based features and posture-based features. The key points-based features group can be further separated in two subgroups: distance domain features and time and frequency domain features. In the key points-based features, the values are obtained from spatial and temporal properties of head, arms, and upper torso key points, while in the posture-based features, the values are derived using the individual poses classified from key points. In other words, the key points based are the primary and posture-based are the secondary group of features. The process of calculating the proposed features is described using a flow diagram. The raw image is first analyzed using the OpenPose API to derive 18 key points, which are then used to perform image classification and determine which student pose appears in the image. Common off-the-shelf camera is used for video stream capture. Here are the pose estimation experiment results. On the left, we can see box plots with accuracy, true positive rate, and F1 score for estimation of body positions with OpenPose on the developed dataset. Overall, the experiment demonstrated a mean accuracy of 96.88%, with a maximum of 100% and a minimum of around 83%. Accuracy is found to be challenged the most in scenarios where a person is standing laterally opposite the camera, as the cores and the limbs are positioned in an unusual way compared to the standard front view. Furthermore, pictures with partially visible parts have shown up to 11.12% lower accuracy levels than the ones with fully visible body parts. The calculated true positive rate has a mean of 94.65%. The greedy parsing algorithm used in the OpenPose model demonstrates efficient parses of body poses and produces high-quality matches. However, most false negatives are a result of missing adjacent key points, since the greedy algorithm estimates the position of limbs by connecting adjacent joints. The value of F1 score mean is 96.16%. with the highest value of 100% and the lowest value of 75%. The lowest performance has been shown in case of partially visible face features, and most false positive comes from imprecise estimation of key points positioning. The model is shown to be highly robust to direction or levels of lighting in the picture. However, there is a potential room for improvement in performances in scenarios with partially visible body parts, particularly face features. To conclude, we have shown that the proposed intelligent agent could be practically developed and applicable in today's world, and have its general performances tested, at least as a prototype. Moreover, it would enable personalization and productivity of education, and overall increase the common quality of teaching. However, some possible future additions would definitely be to precisely define a rigorous experimentation protocol, as well as incorporating other information channels such as gaze direction, eye blink rate, voice recognition, mouse dynamics, pupil dilation, EEG signals, etc. We have come to the end of this presentation. Thank you all so much for listening, and now I would be happy to answer your questions.